Hey everyone, welcome to AI Deep Hallucination. Today's interview question: how do you design an agent's planner to avoid path oscillation caused by replanning at every step?
Wait, what's path oscillation? When I have cursor write code, it does keep changing its mind. Is that it?
Pretty much, picture this: you're driving to work. A normal navigator picks one route and sticks with it. An oscillating navigator recalculates at every traffic light. This side saves 30 seconds, that side saves 30 seconds. You spin in circles for an hour and you're still right where you started.
Do agents really do this? Got a real example?
Last November, there was a real GitHub issue on Copilot CLI. The agent kept calling create file on the same file. Every call returned path already exists, but it wouldn't stop. It just hammered until timeout.
That's just banging the wall to death.
Right? Wall banging is one extreme of oscillation. The academic names vary. Control theory calls it chattering, reinforcement learning calls it dithering, classical AI planning calls it plan instability. The essence is the same: refusing to change what should change or thrashing what shouldn't while task progress goes nowhere.
So what's this interview question really testing? Just don't replan at every step?
We covered this in our previous episode. What does a complete agent architecture include? Every production-grade agent's core is the same while loop plus tool call, react, and plan and execute both run on this loop. The real difference is the frequency at which the planner intervenes.
Right, the skeleton is identical. So what's different in this episode?
This episode is about how to design the planner's intervention frequency inside that loop. That's the watershed between oscillation and stability. And here's the kicker: control theorists, RL researchers, and classical AI planners settled this debate 30 to 50 years ago.
30 years ago? This sounds promising. Where do we start?
Start with control theory. Industry has used MPC for 50 years now, model predictive control. The essence is replanning at every step. At each time point you solve an end-step look-ahead optimization, but you only execute the first step, then resolve at the next step.
Wait, isn't that exactly oscillation? And industry's been using it for 50 years without it falling apart?
MPC is rock solid in industry. The secret is one extra term in its cost function: penalize sharp changes in the control signal between steps. In other words, changing your decision itself has a cost.
That's a neat trick. What's the actual effect?
Here's a household example. Why doesn't a thermostat keep flipping the AC on and off? Because it uses two thresholds: cool at 18 degrees, stop at 22 degrees with a 4-degree dead zone in between. This is called hysteresis. With a single threshold, the temperature jitters around that point and the AC clicks on and off endlessly.
Right, leave a dead zone. Don't switch right at the boundary.
An even harsher example: sliding mode control has a chattering problem. Switching too fast excites the elastic and inertial details that weren't built into the model, and the whole system shakes. The fix is called boundary layer. Replace the hard switch with a smooth curve near the switching boundary, trading a bit of robustness for stability.
How do these tricks transfer to agents?
I'll summarize at the end. Now the second discipline, classical AI planning. In 1975, Sacerdoti at Stanford built a planner called NOAA, proposing the least commitment idea: don't write down anything you don't have to, leave room for environmental feedback to decide later.
Wait, isn't this exactly what today's agent design talks about? Don't lock the whole plan up front, leave room?
In 1996, Tsuneto, Hendler, and now at AAAI compared three commitment strategies: reluctant, eager, and dynamic hybrid. A t-test showed t equals 5.569, p less than 0.005. The dynamic hybrid wins overall, no silver bullet.
So, this is the same debate as today's react versus plan and execute?
Exactly. Then in 2006, Fox introduced the plan stability metric, measuring the difference between two plans, and proved that when something goes wrong, you should patch locally instead of redoing from scratch. This is the ancestor of today's localized replanning. Different name, same idea, 20 years old.
How about the third discipline, RL?
RL has the most systematic research on when to switch decisions. In 1999, Sutton, Prekup, and Singh proposed the options framework. Instead of deciding at every frame, package decisions into an option, with a beta termination function that decides when this option ends and you go back to choose again.
Beta function? Sounds abstract. Can you put it in plain English?
It's a switch the agent carries while doing one thing. Should I stop now and ask the boss again? Beta equals 0 means continue. Beta equals 1 means stop. The replan trigger in LLM agents is the reincarnation of this exact thing. In 2020, Dabney at DeepMind proposed a tweak called epsilon z greedy. Standard epsilon greedy picks a random action with 10% probability at every step. Problem is it can't stick to any direction for more than one step. That's called dithering.
How did he change it?
When exploration triggers, instead of picking just one step, sample a duration z and repeat the same random action for z steps before coming back. This is the ancestor of what LLM agents call the commitment window.
So that's where commitment window comes from.
Right? Then in 2017, DeepMind's FeUdal networks took the layering further. A manager runs slow, sets an abstract goal every few steps. A worker runs fast, executes concrete actions every frame. This is exactly the RL prototype of today's planner-executor split.
After 3 disciplines, looking back at today's LLM agent space, it really does feel like reinventing the wheel.
And the wheel keeps turning. Earliest in 2022, react, reasoning plus acting at every step, highest oscillation risk. 2023, plan and solve, plan first, then execute. Same year, ReWOO, decouple reasoning from observation, only patch locally when a tool fails.
So the paradigms keep getting more restrained.
Right? End of 2023, LLMCompiler went further, turned planning into a dependency graph. A DAG executor runs in parallel along the dependency order. Latency improves up to 3.7 times relative to react. Planner call count drops from once per step to once for the whole run.
Any concrete WebArena numbers?
WebArena is the standard benchmark for testing agents on web tasks. The original 2023 paper had GPT-4 React style at only 14.41%. 2.5 years later, SOTA is at 71.6%. OpAgent, released this January with a 4-module collaborative architecture.
Which 4 modules?
Planner, Grounder, Reflector, Summarizer. The leap from 14% to 71.6% is the most direct real-world evidence for abandoning single-step React and moving to multi-module hierarchical planning.
Over 4 times the leap!
There's a counterexample too. This March, the observability gap paper proved when an agent can only see whether the final output is right but can't see what's wrong inside the code, self-reflection actually introduces oscillation.
Why does reflection make things worse?
Because reflection can't find the true root cause, it can only adjust on surface symptoms, never converging. The paper coined a term for it: persistent failure mode oscillation.
So how do we actually answer this in an interview? I remember in our earlier production agent debugging episode, we covered circuit breaker and retry budget.
That episode was about post-crash recovery, circuit breaker to cut off, retry budget to cap retries. This episode is about preventing the crash at the planner layer in the first place. Let me condense it into 4 tactics. Tactic 1, commitment penalty. When evaluating a plan switch, require the new option to be significantly better than the old, not just slightly. Tactic 2, decision dead zone. Add a hysteresis threshold. Don't switch unless the new option exceeds a margin.
And then?
Tactic 3, 3-tier recovery ladder. First retry with error feedback, then locally patch the plan. Only as last resort do a full replan, no skipping levels. Tactic 4, real planner executor split. Don't let the planner butt in at every step. Let the executor run in steps before checking back.
So these 4 tactics line up perfectly with control theory, classical planning, RL, and engineering. 1 per discipline?
Exactly. We covered in our Claude Code source code episode that CC wins on prevention and LangGraph wins on recovery. Today is about how that LangGraph recovery mechanism is actually designed. Don't make the planner rejudge every step, escalate stepwise only when things break.
So this question isn't really testing whether you've used LangGraph.
Right? It's testing whether you can see that the so-called new papers in the LLM agent space these past 2 years are essentially repackaging what control theory, RL, and classical AI planning settled 30 years ago.
What does the top-tier answer look like?
A top answer doesn't pile on jargon. It says, we're doing control theory's decision dead zone plus RL's manager-worker split plus classical planning's leave room principle, redoing those 3 tricks with an LLM. That one sentence is enough. Alright, that's it for today. Got an interview question you want us to break down? Drop it in the comments. Hit subscribe and we'll see you next time.